Is the matter around us pure? It sounds like a pretty straightforward question, doesn't it? Well, it turns out the way a scientist answers that question is completely different from how you or I might. So today, let's break down how science kind of redefines a word we all think we know so well.
All right, let's start with something you probably have in your fridge right now. Milk. Is your milk really pure? This is where our everyday ideas about purity get turned completely upside down.
I mean, you've seen it 100 times, right? Labels on everything from ghee to milk to juice, all proclaiming they're pure. And we buy this stuff thinking we know exactly what that word means. But what if I told you that from a scientific point of view, none of those things are pure at all?
And this is the heart of the matter. In our everyday language, pure just means, nothing bad has been added, no adulteration. But for a scientist, the definition is way, way stricter. For them, a pure substance has to consist of only one single type of particle.
So what does that mean for our glass of milk? Well, it means it's actually a mixture of water and fats and proteins and a bunch of other stuff. Same thing for seawater. That's a mix of water and salts. Or the soil in your garden. From a scientist's perspective, almost everything we run into in our daily lives is actually a mixture.
Okay, so this brings us to the first major way scientists start to classify, all matter. Everything, and I mean everything, is going to fall into one of these two buckets. It's either a mixture or a pure substance.
So on one side, you've got your pure substances. Think of something like table salt or sugar. Every single tiny particle in that sugar bowl is chemically identical. Then, on the other side, you have mixtures. These are just two or more pure substances that are physically jumbled together. Like when you dissolve that salt in a glass of water.
So the big question is, how do we tell them apart? Well, the ultimate test is separation. You can get that salt back from your salt water just by boiling the water away. That's a physical process, right? But you can't break down pure salt into sodium and chlorine just by boiling it. Nope, that requires a chemical change. That's the key difference.
All right, now let's dive deeper into the world of mixtures, because it turns out not all mixtures are created equal. Scientists actually group them into three really distinct categories based on how their parts behave. And this is where things get pretty cool.
First up, we have solutions. Now, these are the perfectly blended mixtures. Scientists have a fancy word for it, homogeneous. The particles are so ridiculously tiny you can't see them, and they're spread out so perfectly that a beam of light just passes right through without a problem. In fact, the very air you're breathing right now, that's a perfect example of a solution.
Okay, now let's go to the complete opposite end of the spectrum. Here you'll find suspensions. These are heterogeneous, which is just a sciencey way of saying you can totally see the different parts. Just think of muddy water. The dirt particles are big, they definitely scatter light, and if you just leave that glass alone for a while, they'll all settle down to the bottom. That tells you the mixture is unstable.
And now for the fascinating middle ground, colloids. A colloid, like our good old friend milk, looks totally uniform to the naked eye, just like a solution does. But, and this is the cool part, its particles are just big enough to scatter light, and that scattering reveals that it's actually a heterogeneous mixture. They're stable though, they won't settle out like a suspension.
And that light scattering trick has a name. It's called the Tyndall effect. You've definitely seen this before. If you've ever seen those beautiful sunbeams shining through a forest canopy, or through a dusty room, you've witnessed the Tyndall effect. You're not actually seeing the beam of light itself. What you're seeing is the light being scattered by all the tiny particles of dust or water hanging in the air.
Okay, so we've pretty much covered mixtures. Now let's jump back across that dividing line and explore the other side of our classification chart, the world of pure substances.
The absolute simplest type of pure substance is an element. This is matter in its most basic, fundamental form. You simply cannot break down something like pure iron or pure oxygen into anything simpler using a chemical reaction. These are literally the universe's building blocks. So what happens when you start combining those building blocks? You get a compound. But this isn't just a simple mix and match. The elements are chemically bonded together in a very specific, fixed ratio. Water is always two hydrogen atoms bonded to one oxygen atom, H2O. If you change that ratio, it's just not water anymore. This distinction between a mixture and a compound is so important. It's really worth seeing it in action. So let's explore what really happens when you just mix two elements together versus when you chemically combine them into a brand new compound. Okay, so let's imagine a little experiment. We have two groups. Group 1 just takes some iron filings and some yellow sulfur powder and stirs them together. That's it, they've made a mixture. Now, group 2 does the same thing, but then they take it a step further. They heat their mixture strongly. This causes a chemical reaction. They've made a compound.
And just look at the results, they're completely different. The mixture still looks like, well, iron and sulfur. You can even physically pull the iron right out with a magnet. But the compound, it's a totally new, uniform black substance. And get this, it's not magnetic anymore. The original properties of the iron and sulfur are just gone. And that's the key takeaway. The mixture kept the properties of its parts, but the compound has entirely new ones.
Okay, before we wrap this all up, I want to show you one last fascinating property of mixtures. Take a look at this number, 167 grams. What on earth could that possibly mean? Well, that's the amount of a salt called potassium nitrate that you can dissolve in a bit of water when it's hot, around 80 degrees Celsius. But if you cool that exact same water down to just 10 degrees, its capacity to hold that salt plummets to only 21 grams. It's just a really powerful reminder that the properties of a mixture aren't always fixed. They can change dramatically with something as simple as a change in temperature.
So there you have it. Your world reclassified. We started with a simple everyday word, pure, and we ended up with this really powerful framework for understanding pretty much everything that makes up our entire universe.
And here it is, the whole shebang in one place. All matter splits into two main paths, mixtures and pure substances. Mixtures can be totally uniform, like solutions, or they can be non-uniform, like suspensions and colloids. And on the other side, pure substances can be those fundamental elements, or they can be chemically bonded compounds. This is basically the map that scientists use to classify the world.
And now you can use this map too. That coffee on your desk, what do you think? Is it a solution or maybe even a colloid? The glass window you're looking through, the air you're breathing, how would you classify them now? See, the world looks a little different once you know how it's all put together.